quiz? Okay. Here we go, I think. Are we recording? I was supposed to get a little ding noise. Oh, I've got it on mute, that's why. My favorite student, good old Anne Serkey, she gets everything right. Number one, a half mark for each answer. That's why it's worth a total of 2 marks. A skydiver is in free fall. I mentioned that I jumped out of an airplane. He's been falling long enough to hit terminal velocity, so he's no longer accelerating. Which of the following statements are true? A, there are no forces acting on the skydiver since he's not accelerating. True or false? Gravity is definitely acting on him. The magnitude of the gravitational force is equal to the magnitude of the force of air resistance. I think that's true. That's why he's not accelerating. The net force on the skydiver is equal to 0. That has to be true because if he was accelerating, the net force wouldn't be 0. That's Newton's first law. If he's not accelerating, you know the net force is 0. Skydiver is slowing down. No, that would be accelerating. So half mark for each of those. Number 2 says, find the acceleration of the entire system. You know what? There's more than one mass. I'm going to label my forces. I'm going to have M1G, normal force number 1, tension. M2G, normal force number 2. Tension is slowing this mass down. And we have an applied force of 45 newtons to the right. And now I can find the acceleration of the system. Who's winning? The applied force. And then I'm going to walk along the rope. So I'm going to get the applied force minus tension plus tension, and that's going to be the mass of both of them times A. Why the mass of both? Because I have forces for more than one mass. Yay. I'm going to get the acceleration equals the applied force divided by both masses. It's going to be 45 divided by 10 plus 15. Oh, I could do that in my head. 45 divided by 25. It's the same as 9 over 5. 1.8? Yes? And it's an acceleration meters per second squared. If you got that, 2 out of 2. Otherwise, if I was marking this, I would give you 1 mark if I saw that equation. I would give you a half mark if I saw that equation, and then a half mark for the answer. But again, if you got the right answer, 2 out of 2. Find the tension between the two masses. Courtney, either mass will work, but I think I'm going to target mass 1. Because if I target mass 1, the equation is going to be tension, no loser, equals MA, M1A, where M1 is 10 and A is 1.8. And holy smokes, I can do that in my head completely, 18 newtons. You would get the same answer if you used mass 2. You would go applied force minus tension equals M2A. Tension equals M2A. Sorry, tension equals applied force minus M2A. And solve. 1 mark for that. Half mark for the numbers. Half mark for the answer. But again, if you got the right answer, 2 out of 2. Number 3 is the same as question number 2, except I included friction. Oh, and I said change the pulling force from 45 to 60 newtons. So I said, okay, now that's going to be 60 newtons. If you run the numbers with 45, you'll find it doesn't accelerate because friction is too big. But now there's friction, so now I would also have friction force number 1 and friction force number 2. Otherwise, the free body diagram is the same. I'll just add it to my diagram. Now my equation is going to look like this. Who's winning? The applied force minus tension minus friction force number 2 plus tension minus friction force number 1. That equals M1 plus M2 times A. I like that. To get the A by itself, it's going to be divide by M1 plus M2, and it's going to be the applied force minus friction. Well, friction is mu times the normal force. minus friction. Well, friction 1 is mu times normal force number 1. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which force? mg. That ends today, by the way. As of today, most of the time, mg is not going to be equal to the normal force. As soon as we start going on a slant, which is going to be today's lesson, don't you dare assume that the normal force is mg. It'll be something else, and you'll have to do some thinking, okay? But for now, we are able to say that this equals mg and that this equals mg. m2g and m1g. So, it's going to be 60 minus 0.12 times 15 times 9.8 minus 0.12 times 10 times 9.8 all over 10 plus 15. You know, arguably I should be able to do that in my head. It's dividing by 20. I'm wearing a pirate costume. I'm dumber. 0.12 times 15 times 9.8 minus 0.12 times 10 times 9.8. Double check my typing. Missed the 1 up there. Divided by, I'm going to be bad and add those in my head, 25. Do you get 1.224, 1.22? And it's an acceleration, so it's going to be meters per second squared. Meters per second squared. Full marks if you got that. Otherwise, for 3 marks, I would give you 1 mark if I saw that, 1 mark if I saw that, half mark for that, a half mark for the answer. I may have told this story before. About 7 or 8 years ago, Mr. Kamosi and I were teaching Math 12 together. We took turns making up the tests, and I had made up the trig test, and I had made up an answer key, and I'd given the answer key to Mr. Kamosi, and a kid stole it from his desk and used it to cheat. And the reason it was so obvious that this kid had used it to cheat was on his answer that he handed in. He had all these 1s and 0.5s all circled. He'd actually copied my whole marking scheme as part of his cheat. He had no idea what he was doing. He'd memorized the whole page. Oh, and Mr. Kamosi, when he'd photocopied his version of the test, had swapped 2 pages. So the student that was cheating had perfect from this page, but on this page, and perfect from this page, but on this page. Don't cheat. By the way, so we caught him, we gave him a 0. Next year, if you cheat and you get caught, what happens in university? You get turfed. You get no tuition, no refund, you're gone. And they're much better at catching it. Do not think you can get away with it. Speaking of cheating and tension, let's find some tension. It says find the tension between 2 masses. You could use mass 2. I still think mass 1 is cleaner, so I'm going to go use mass 1. For mass 1, it would be tension minus friction force 1 equals M1A. It's going to be tension equals M1A plus friction force 1. It's going to be M1A plus mu times the normal force. I don't know the normal force. Oh, but look, M1G. So it's going to be M1, which was 10 times 1.224. I'll use the full value, plus, what was mu? 0.12 times 10 times 9.8. 10 times answer button plus 0.12 times 10 times 9.8. And I got, oh, nice, 24 newtons, yes? Again, if you got that right, full marks, 2 out of 2. Otherwise, I would probably go 1 mark for that, half mark for that, and a half mark for the answer. Elevator questions. It's asking you to find the scale reading. No, it's not. Yes, it is. No, it's not. What's it really asking you to find? Whenever I talk about a scale, which force am I really talking about? The normal force. I'm going to do a free body diagram. We're accelerating up, so I have gravity down, but since we're accelerating up, normal force must be winning in part A. It's going to be normal force minus mg equals ma. The normal force equals ma plus mg, or mg plus ma. It's going to be 75 times 1.6 plus 75 times 9.8. $855 newtons. 2 marks for the right answer. Otherwise, 1 mark. Oh, change colors, Mr. Duke. Otherwise, 1 mark for that, half mark for that, half mark for the answer. B, you know what? Since we're accelerating downwards, I'm just going to imagine the correct free body diagram from the one that I've already drawn. Who would be winning? mg. Minus normal force equals ma. I guess to get the normal force by itself, I'll plus that there, minus that there. I'll get mg minus ma equals the normal force. So it's going to be 75 times 9.8 minus 75 times 1.25. You get 641 newtons? 2 marks. Again, 1 mark for that, half mark for getting the normal force by itself, half mark for plugging in the numbers correctly. You can see, by the way, Taylor, really, I'm not that interested in the answer. I'm interested in the method. You can make math mistakes and still get most of the marks on a big question, right? C. Moving up at a constant velocity, what's the normal force? If you're moving up at a constant velocity, what's your acceleration? Ah, really, this is telling me that A equals 0. We're moving up, so I might be tempted to let gravity be the winner and normal force be the loser, but it's going to be equal to 0 because m0, 0. In fact, I'm going to argue really the normal force is just going to be equal to mg. I think I said it, but it bears repeating. This is what Einstein said. Einstein said there's no experiment in the universe that can prove whether you're moving at a constant speed or at rest. We can't prove that. We can prove you're accelerating. It's easy to detect acceleration, but the difference between constant speed and at rest is all relative. It's why he picked the phrase relativity for both of his theories. By the way, are you guys moving right now or are you at rest? We are moving. Many ways. Earth is rotating. Not only is the Earth rotating, it's also moving around the sun. Not only that, the sun itself is moving through the galaxy. I mean, we're moving like crazy. But because those speeds are constant, we can only tell that we're moving relative to the stars that we observe. We have to look at something else. 75 times 9.8, I can do that in my head, because 75 times 10 is going to be 750. It's going to be 750 minus 15. 735? Yeah. Oh, man. I know I'm wearing a pirate costume, but I better be able to do some basic math. Half mark, half mark, half mark. What if the elevator is in free fall? What would the scale read? 0. So how heavy would I feel? I would feel, and this is why we call it apparently weightless, I would feel an apparent weight of 0. When I jumped out of an airplane, I felt no weight. Now, mg was still there, but again, what I want you to realize is what you think of as your weight is the floor or the chair is the normal force pushing up against you. Take that away and you'll freak out, or you'll pay good money for it on an amusement park ride. How could I prove that it's, by the way, if you wrote 0, 2 out of 2. But I had somebody last class say, how would you prove that? Well, I'd probably go something like this. If I'm accelerating downwards, who's winning? So I might be tempted to go gravity minus normal force equals ma, and then I would plus that. So I would get this. Normal force equals mg minus ma. What's g? 9.8. What's a? Also 9.8. I would get 75 times 9.8. Take away 75 times 9.8. I would get something take away itself. What's anything take away itself? So if you needed to do a proof, there it is. But if you were clever enough to go straight there, 2 out of 2. Can you give yourself a lovely score out of 19? And now is the chance to come lawyer with me. Last day, we looked at the Atwood machine. Really, what I wanted you to realize was this approach that I've given you, labeling your forces, asking who's winning. Really, I'm saying which way is accelerating, letting the direction that we're accelerating, Adrian, be positive. Don't always let up be positive and down be negative. Let the acceleration directed be positive because the math works so much nicer, and that means our 9.8 is always going to be positive when we put it in. We can figure out a lot of complex questions. Initially, when we looked at these contact force questions, for example, At first it was like, what's going on? But I hope I convinced you, Dylan, actually with a little bit of cleverness, still works. Newton's laws and a good free body diagram and winner minus loser still bails us out. I gave you some questions to try. One of the questions that I made optional was this scholarship one. If you go to pitmath.com, you know what, Mr. Dewick? I think I have to go like this. Pause. You go to pitmath.com, click on Physics 12, and then go to where the lessons are. So under block A, you guys have seen this page, I hope. Under block A, C, and D, the very, very bottom, I've put a full YouTube solution to number 9 if you want to look at it. Again, number 9 is not a question that would appear on the written section of your test. It's too tough. You know what? Those scholarship questions, if you're wanting an idea, I've told you on every test on the multiple choice, I'll put a curveball. A good example of the difficulty level would be the ones on your big review package that are called scholarship questions, or the ones in your homework that I tell you are from old scholarship exams. Those would be an idea of a good nasty question. So aside from number 9, any questions from the homework company to go over? Rest should have been okay, I think, yeah. Even something like number 8, I've never done one like that, but hopefully the key for number 8, Kareem, is to realize that right there. It's at rest. If it's at rest, what's the acceleration? Oh, the equation became way easier. In fact, that's the only way that you can solve for a normal force. First of all, there's no way the 3.2 could be accelerating up, because that would mean the 5.0 was going through the table. That's not going to happen. If the 3.2 was accelerating down, hey, there wouldn't be any normal force because the 5 would be leaving the table. So the only way I can ask that question is if the acceleration is at rest. So we're good. If you have that done, you can hand that in. And today, Physics 12 begins. We're going to go right to the tone. Next class, I'll finish off the lesson and give you some homework. So for you guys, for your final grade 12 Halloween, no homework from your physics teacher. You can go trick-or-treating if you want. Stupid kids. Oh, here we go. You ready? You're going to want a calculator out. You're going to want a brain out. You're going to want to stop talking. Here we go. Today, we're going to incline things. We're going to try and see if we can reason our way to certain patterns. It says this, example 1, suppose a person is standing on a ramp. And in fact, on the ramp, they're standing on a scale. Let's make it a scale that measures in newtons, not kilograms. And they're attached to a rope. As the ramp gets steeper and steeper and steeper, as the angle increases, what happens to the scale reading? Now, when I'm talking about the scale reading, which force am I really talking about? Okay, so really what I'm saying is what happens to the normal force. There's no change. Does it increase or does it decrease? And convince me. What do you think? As the ramp gets steeper and steeper and steeper, what would this person notice was happening to the scale reading that they were standing on? Yeah.
It would decrease.
Decrease? You're right. Convince me.
Because as the angle increases, he's relying more on the tension of the rope than normal
Okay.
to hold him up.
I have no problem with that explanation. One of the things I'm trying to do at the beginning of the year is give you tricks of the trade, how you can do a proof. One of my fallbacks for something like this is to look at the extremes. What's the smallest angle we could have in degrees? Obviously, 0 degrees. What's the biggest angle we could have in degrees? Obviously. Let's look at 0 and 90 degrees. So I'm going to write down here where it says for a proof. I'm going to say if theta equals 0 degrees, underneath that I'm going to write if theta equals 90 degrees, my two extremes. If we're flat, if theta equals 0 degrees, what would the normal force be reading in terms of the free body diagram? What would it display? Yes, comma, the normal force just equals mg. You okay with that? What if it was vertical and the guy was dangling from the rope? What would the scale read? 0. So at 90 degrees, the normal force reads 0 newtons. Then, John, the third assumption I'm going to make is that this change occurs smoothly. That doesn't magically jump around like crazy. You went from maximum normal force, mg, to 0. I think you decreased. It's the only way you could end up at 0. You're getting smaller. Okay? That's what I'm just going to write. Therefore, normal force, and my abbreviation for decreases is an arrow pointing down. You know what my abbreviation is for increases? An arrow pointing up. Okay. This trick of, Courtney, going to the extreme values can be really, really handy. If they give you a question and there's something changing, don't look at the situation that they're talking about at an angle, because that's the toughest. Go to minimum angle, maximum angle. Go to minimum voltage, maximum voltage. Go to minimum amperage, maximum amperage. Look at it there, and it's got to change smoothly to go from situation 1 to situation 2. The second question, example 2, same situation, but instead of looking at the scale reading, the normal force, what happens to the tension as the rope gets steeper and steeper and steeper and steeper? What happens to the tension? Yeah.
It increases.
Increases? Convince me. You know what? I'm going to go, same argument. I'm going to copy this. Now I'm going to have to change a little bit of stuff, but I'm going to start out by writing 0 degrees and 90 degrees, but I'm not interested in the normal force. Let's get rid of that. At 0 degrees, when the ramp is flat, wouldn't the rope be slack? What would that suggest about the tension? Okay. What about at 90 degrees when he's dangling? What's the tension equal to? I can even tell you exactly. Yep. So if you're going smoothly from 0 to maximum, therefore tension must be increasing. Why is tension increasing? Because gravity's component is increasing. Why is normal force decreasing? Because another component of gravity is decreasing. And this is going to lead us to today's lesson. On the next page, we have a ramp. What I want you to realize is that anytime you have an object on a ramp, gravity is doing two things. Part of gravity is holding it onto the ramp, is squeezing it onto the ramp. We call that the normal, well, it's not the normal force, but it'll be the same size as the normal force, because look. Another part of gravity is sliding it down the ramp. So what I wrote here is, for objects on a ramp, the force of gravity partly pulls the object onto and partly pulls the object down. Squeeze and slide. Here's how we're going to break gravity up. And I'm going to strongly encourage you, until you get good, Taylor, do it exactly my way. Okay? First of all, let's do a free body diagram on this box. What are the forces? Get the obvious one. I'm going to encourage you, draw gravity nice and big so that it actually goes through the floor. And put the mg on the pointy side of your line, next to, on the same side as the pointy part of the ramp. Always put the mg on the same side as the pointy part of the ramp. Trust me. Did I say ramp? What I really meant was there's an angle right there. Did I say angle? What's this a job for? Components. The real question is, how am I going to break this up? We have two options. We could break up all the other forces so that they were dead vertical and horizontal to match gravity. That's a lot of work. Instead, we're going to break up gravity. We're going to break gravity up into a component that's perpendicular to the ramp and a component that's parallel to the ramp, where that's a right angle right there. Okay? And we're even going to label these. We're going to call this one MG perpendicular, and the symbol for perpendicular is an upside down capital T, two perpendicular lines. And we're going to call this one down here MG parallel, and the symbol for parallel is two parallel lines at a slant, like that. Okay. Then, now those red dotted lines wouldn't appear on my free body diagram because they're components. The blue mg is the one on my free body diagram. However, is this block sinking into the ramp like quicksand? No. Is it flying into the air like Superman? So there has to be a normal force. Now remember, the normal force is going to always point out at a right angle from the ramp. How big is it going to be? This big. The same size as mg perpendicular. perpendicular, because mg perpendicular pulls it in, the ramp pushes out. So I'm going to go back to blue because this is on my free body diagram. I drew that line about the same length as my mg perpendicular. Then, if there was friction, well, it would depend. If the ramp was sliding down the hill, friction would be pointing up the hill. So I said if the mass was sliding down the hill, friction would be pushing up the hill. If the mass was sliding up the ramp, friction would be pointing down the ramp. So the key is we're going to break gravity up into a perpendicular and parallel component, and the perpendicular component will tell you the normal force. Look, 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 look. In terms of the other forces that act, there's going to be a normal force. There it is. It's perpendicular to the surface, and if it's rough, there's going to be friction. So, example 3 says, draw a force diagram for an object on a rough ramp. Rough, I mean there's friction, and in situation A, we're sliding down the ramp. Okay. What are the forces acting on this block? Get the obvious one. Draw it pretty big. I encourage you initially go through the floor because you want to hit the floor at a nice 90-degree angle. And put the letters mg on the same side as the pointy part of the ramp. By the way, if you don't, you end up with the mg inside your triangle and it makes the trig tougher. I'm going to break this gravity up into components. Now, the components I'm going to do as dotted lines. Courtney, that's my way of telling the marker the components actually aren't part of the free body diagram. The components are included in that mg that I've drawn straight down. But I'm going to break it up into a perpendicular component, mg perpendicular, and then a parallel component where the 90-degree angle, the right angle, is right there. mg is the hypotenuse. And Kareem, by parallel, I mean this line will be parallel to the ramp. That and that will be parallel. Kareem, is this mass sinking into the ground like quicksand? Is it flying off the ramp like Superman? So there's going to be a normal force. Look up, not pointing straight up, perpendicular to the ramp. So it's going to come out this way. How big will it be? It's a Newton's third law counterpoint to this one. So it's going to be the same size, I'll eyeball it, as mg perpendicular. Ethan, which way is this box sliding? Which way would friction be acting then? Up the ramp. I can't even say left because left would be that way. Friction's not acting that way. Friction is going to be pointed that way. Now, by the way, what's pulling this down the ramp? Don't say mg because it's not. What force is pulling this straight down the ramp? I'll give you a hint. It's the force that's pointing straight down the ramp. It's not mg. mg is not pointing straight down. Sorry? mg parallel. What's pulling it down the ramp is this component. Now, if friction is bigger than this, it won't slide down the ramp. This is what happens when cars park on a hill. If this is bigger than that, skiing, for example, if friction's really small, well, now you'll slide down the ramp and you'll accelerate, not at 9.8, but at this component. The 3 blue lines are the free body diagram. The red dotted lines are if I had to solve it, what I would do next. Also, the red dotted lines help me figure out how big the normal force should be drawn. What if instead of sliding down, we're sliding up the ramp? Maybe we're pulling it up the ramp. Well, what are the forces acting on this? Get the obvious one. I'm going to break mg up into a perpendicular component. By the way, a common mistake that I see, don't write this down, look up. Kids draw mg fine. And then they make the perpendicular component this long, and they make parallel to the base. No, no, no. It's going to be perpendicular, I'm going to stop when I get right to about there. That is mg perpendicular. And there is mg parallel. The right angle goes there. Is this box sinking into the ground like quicksand? No. Is it flying into there like Superman? So something has to be pushing it out of the ramp. There has to be a normal force. How big is the normal force? This big. This big. This big. That one I eyeball, I try and get it close. I think that's pretty close. Ethan, which way is this block sliding? Which way would friction be acting then? And you'll notice this time, Ethan, there are two forces slowing it down. Friction is slowing it down, pulling down the ramp, and gravity is slowing it down. This is why trying to slide something uphill, it comes to a stop pretty fast. Or you can't get it going at all. That's why it's much harder to pull stuff uphill than it is downhill. Is that okay? Yeah. So, turn the page. Which of the following is the best force free body diagram for a mass that is, here's a word I would probably underline, a phrase, at rest on a ramp? Other Ethan, if we're at rest, what am I really telling you? A is equal to?
0.
Okay, which means all of the forces are, I'm looking for a word that begins with the letter B.
Balanced.
They're balanced. Which of those is the correct free body diagram? A or B? Or, to be honest, I would answer it the other way. Which of those is the wrong free body diagram and can't possibly be at rest? And then pick the other one. Which of these can't be at rest? Why can't B possibly be at rest? Why is A the correct answer? Yeah, in your face. You know what? Let's break it up into components. Okay? Let's look at B for a second. And I'm going to take gravity. Clearly, gravity is the one pointing down. I'm going to break it up into components, which would look like this and like that. Yes? Sorry, this should be a dotted line. Now, Prith, do these two, this one, the normal force, and this one cancel each other out? Say yes. Which way is this pointing? Down the? Is there any force pointing up the ramp? Is it possible for this to be at rest then? Can't be. Here, we would break gravity up, and we would say, you know what? These two must be equal to each other. Friction is exactly canceling out the parallel component of gravity. Has to be A. Okay? So explain your answer using principles of physics. Only A has friction cancel out mg parallel. Instead of writing the word parallel, you guys can write mg with two slanty lines, but I don't know how to do that on my computer. B can't be at rest. Forces are not balanced. We're going to analyze this diagram once, Nat. And if you always draw it the same way as me, what we're going to do is we're going to memorize where an angle ends up and not bother rederiving it every time. Okay? And then if we do that, then all of our trig will be the same. We'll memorize a couple of shortcuts. The fact that I'm telling you to memorize stuff, and you know how much I hate memorizing things, probably suggests it's really worth memorizing this stuff. So here is our diagram. I've got good old mg down. I've got mg down. Here's the angle theta that they've given us. I'd like to figure out where that angle ends up in this triangle here. And I'm going to do a proof just once. After that, we're going to memorize where it ends up. We're going to skip the proof. First of all, hey, how big is angle 1 right there? What's that look like to you? Let's write that down. What does every triangle add to? 180. So if this is 90, what's left for these two? Also, so if this is 30, how big is this one? Yep, say it. 60. If this is 40, how big is this one? If this is 70, how big is this one? If this is theta, how big is this one? Angle 2 is whatever 90 degrees minus theta ends up being. If theta is 30, 60. If theta is 45, 45. If theta is 60, 30. But they got to add to 90. You okay with that? Then under the new curriculum, you folks haven't done much geometry, and you've never seen this Z pattern here. We call these alternate interior angles. And it says this: if you have a letter Z and the top and the bottom of the Z are parallel, which they are because I drew it that way, the two interior angles are the same. In other words, what you can write is angle 3 equals angle 2, which is 90 minus theta. Adim, how big is this angle right here? 90. So, here's my proof. If that's 90 and that's 90, if that angle and that angle are the same, what can you tell me about these two angles? You're right. Yep. Angle 4 must be theta. So I'm not going to prove that again. Instead, John, what you're going to see me do when I draw my diagram is I'm going to do this. I'll color in down here, and I'll just color in right there, and that's my way of saying, hey, that angle's that angle, and reminding myself of that each time. If you draw things in a different order from me, that won't work. So, hey, draw them in the same order I do. I always do perpendicular, then parallel. Let's actually crunch some numbers. Example 6. Find the acceleration of this mass sliding down a frictionless 25-degree ramp. It's frictionless ice. Okay. Marcus, what do they want me to find? I know I caught you zoning out. I got my evil eye. I got my evil eye on you. What do they want me to find, Marcus? Good. Hey, is there angles? Is this a force question? What's the first thing I'm going to do, folks? Yep, label my forces. Rather than do a separate free body diagram, since it gave me the lovely picture, I'll label this. So, what am I going to do first? What are the forces acting on this 2-kilogram mass? Okay. Can I give you some advice? Until you get good at this, draw your MG nice and big, maybe even hitting the floor at a 90-degree angle so you can see it. And always put the MG on the same side as the pointy part of the ramp. In this case, it'll be on the left side. And now I'm going to pause. I'm going to break this MG up into components. How do I know? Because there's angles. What are the components going to be? There's going to be a perpendicular component. And I'm going to stop when I get right to about here. This is going to be MG perpendicular. And there's going to be a parallel component. And I want this parallel to be pretty close to the same slant as the ramp. This is going to be MG parallel. And the 90-degree angle goes there. Is this sinking into the ground like quicksand? Is it flying into the air like Superman? So there's going to be a normal force. That would be too big. That would be too small. Draw, 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 draw. For me, I'm going to stop right about there. That looks about the same length as my perpendicular component. There's my normal force. Friction? Okay. Perpendicular. Upside down T is perpendicular. So it's hitting this ramp at a lovely right angle, which is also why you get a lovely right angle right there. Okay? So perpendicular, and what's this one stand for, Kareem? Parallel. Okay? Marcus, which way is this ramp? Sorry, I did it again. Which way is this block sliding? It's not to the ramp, not sliding left. 3 words. Something the something. 3 words. Something the ramp. 3 words. And I'm going to be fussy. Don't say down because you're going to think it's that. Which way is it going? Down the. Which way is accelerating? Say it again. One more time, I'm not to make fun of you, but for a good reason. Which way is accelerating? Who's winning? The only force that's pointing down the ramp. Don't you dare say mg. Which force is winning? Ah. Which force is losing? Anything that's pointing up the ramp. Is anything pointing up the ramp? No loser. What does that always equal, Marcus? What has our winner minus loser equaled since Physics 11? Still works. We need to do some trig. I'm going to pick this triangle up and I'm going to draw it right over here. So over here, I'm going to draw mg, mg upside down t perpendicular, and mg parallel. Oh, I can do one more thing. Once you've written that down, all of you look up for a second. All of you right now, color in the bottom down here, color in the top up there. Those two angles are the same, which means this angle right here is 25 degrees. That's the proof that we did on the previous page. The bottom pointy ramp angle is going to be in the very, very top if I go perpendicular than parallel. That'll always work. Hey, this mg, opposite, adjacent, or hypotenuse? Hypotenuse. This mg parallel, opposite or adjacent?
Opposite.
Which trig function? Sine. You're going to get this. Sine, I'm going to do this generically, of theta, 25 in this case, but of theta, whatever the angle is of the ramp, equals opposite over hypotenuse. Let's get the mg parallel by itself, because Marcus, that's what you told me I want up in my force equation. Yes? Mg parallel. How would I get the mg parallel by itself? I guess mg parallel is going to be the same as mg sine. Student of mine about 4 years ago came up with a stupid way to remember this. Kareem, what's the symbol for parallel? To what? Loud and proud. To what? 2 lines is sine. 2 lines is sine. That's what they came up with. Mr. Dewick, parallel is always going to be sine. 2 lines is sine. Unless gravity magically changed and we're not in a weird universe. So if you draw the triangle my way, if you put the same theta that I do up there, mg parallel is going to always be mg sine. Now, if you forget, Taylor, I've just shown how you can derive it. I'll be honest, this is a good enough shortcut that we'll commit it to memory because, oh, it's nice. By the way, if mg 2 lines is sine, what do you think mg perpendicular is going to be? Of course it is. Yes, of course it is. Not cosine, obvious, of course it is. Okay. So, Marcus, over here, I can replace this with mg sine theta equals ma, because parallel is sine. Now, something kind of neat happens. Is there an m in everything on the left-hand side? Is there an m in everything on the right-hand side? We already got the a by itself. It's going to be 9.8 times the sine of what angle in this case? More specific in this case? Yep. You go. Oh, by the way, built-in error check. If this ramp was vertical, what's the fastest you would be accelerating at in free fall? Ditch the negative, but 9.8. Is this vertical? We're going to get an answer less than 9.8. If you don't, you've messed up. So 9.8 sine 25. 9.8 sine 25. I get 4.14 meters per second squared. Also, you've noticed, Adeem, that although acceleration is a vector, it's become pretty obvious in this unit. All I care about for the most part is the magnitude, because we've got stuff on pulleys moving in different directions, or even, how would you describe this? I guess you could say as a direction down the ramp, but like north of east, or it doesn't really work all that well because the top of a ramp isn't north. We're looking at it from the side. So I just want the magnitude. If I ever want a direction, you better believe in the question I'll make sure I put in brackets magnitude and direction. Otherwise, magnitude. Gesundheit. Is that okay? Let's do one with friction. I like example 7, I like example 7, I like example 7, I like example 7. Example 7 is a nice question. Why would I say that, Prith? Okay. Except here's what I don't like about it, to be honest. I wouldn't do part A first. I would jump straight to part B. In fact, preview of coming attractions. Courtney, in example 7, part B, what are they asking me to find? If I ask you to find acceleration, I would have no problem giving that part A, and then for part B saying, oh, if VF is thus and such, find the distance. Or if VI is thus and such, now that you know the acceleration, find time. All the physics 11 stuff, VF equals VI plus AT, and VF squared equals VI squared plus 2AD, and D equals VIT plus a half AT squared. That's all fair game, and that would also be a nice way to bring in stuff we've already done. You can definitely expect on your test, I'll give you a ramp question, and instead of saying find the acceleration, I'll ask you to find a distance, or a final velocity, or a time, or an initial velocity. And even though that's what the question says, you're going to spend most of your time finding the acceleration. Little hint. Anyways, here, John, what does part A want me to find? How am I going to start out? Free body diagram, label my forces. Here we go. John, what are the forces acting on this 5 kilogram mass? Get the obvious one. Again, let me encourage you. Every year, I see kids, they go like this, mg, and then they draw their components, but that triangle is so small, they can't easily spot mistakes. So I strongly encourage you for at least the gravity triangle, draw it big, and the mg goes on the same side as the pointy part of the ramp. Did I say ramp? I'm going to break mg into its components. I'm going to break it up into a perpendicular. Would stopping right there be correct? No. I'm eyeballing it. I probably want to stop right around there. That's going to give me a parallel component. So here, also Courtney, because I think you're one that wasn't doing this earlier, put the arrow on there to say that's pointing down, that's mg perpendicular. Then put an arrow right there. That's mg parallel. That's 90 degrees. Oh, and the last thing, Michael, color in the tip of the ramp, color in the tip of our triangle. That's where the 35 is going to go. Not in the bottom part, in the top part from that proof on the previous page. What else, John? Normal force. How big? Same size as perpendicular. So if and I'm going to do it in blue because it's part of the free body diagram. It's not a component. About like that. Again, perpendicular to the surface. What else? Is there friction? Which way is this mass sliding? Down the ramp. So which way will friction be pointing? And I'm going to make the assumption that friction is smaller than the gravitational component because it seems to suggest it's sliding down. So far, so good, my friend? Okay. What is part A asking me to find? Well, friction, the equation will never change. Friction equals what times what? Mu times the normal force. Write that down. I don't know the normal force. Oh, but look. There is another force the same size as the normal force. And it's not mg. Friction is going to be mu mg perpendicular. Which trig function was perpendicular? Parallel was 2 lines. That one was sine. So which trig function is the perpendicular component going to be? Of course it is. If you want me to do it generically, it'll be mu mg cos theta. By the way, the only way that would change would be is if instead of giving you the angle of the ramp, they gave you this angle up here. I've never seen that. I've never seen that in any textbook anywhere. So I guess technically I'm cheating a bit, but I'm telling you all year on your test and your homework, I'll give you this angle down here, and in all of my textbooks where I steal questions from, I can't recall a single time that for some reason they gave the angle up. You measure from the ground up. It's a ramp. So, okay. Hey, now we got plug and chug. John, what's mu? I don't know. What's mu with you? No, what's mu? 0.2. Mass doesn't cancel this time. 5 times 9.8 cosine of 35. Point 2 times 5 times 9.8 cos 35. And I get 8.03. Is that right? Yeah? Okay. 8.0303, and it's a force. Units? Newtons. Newtons. All right. Hedrick, what does B want me to find?
Acceleration.
Okay. Which way is it accelerating?
Down the road.
Who's winning? Don't say MG.
G parallel.
Nice. So you ready? I'll do the acceleration down here. I've just decided that's my winning direction, down the ramp. Are there any other winning forces pointing down the ramp? No. If there were, plus signs. Yes? Are there any losing forces pointing up the ramp? Oh, loser. What does that always equal? No. What does winner minus loser always equal? MA. Now, I realize John and I have just calculated friction in part A, and I would have no problem if you dropped the 8.03 down, but I'm going to do this algebraically, just show you something kind of cool, and it explains something that you may or may not have noticed when you're skiing. mg, oh, you know what? I'm going to rewrite this. Friction is, that's what you said, mu times the normal force, that equals ma. I would say to you, I don't know the normal force, but then I would say, oh, but look, I know another force the same size as the normal force. So we would say this, mg parallel minus mu mg perpendicular equals ma. You okay with that? Hedrick, mg two lines. Which trig function was that one? Do you remember? Two lines is going to be sine. I'm going to get this. mg sine theta minus mu. What about mg perpendicular? Of course it is. Don't forget the m. Don't forget the g. Cos theta. And that equals ma. Hedrick, is there an m in this term? Is there an m in this term? Is there an m in this term? Is there an m in every term? You know what we can say about the m's then? They can't. In fact, I could have really canceled them on this line, but that scares kids for some reason. So here it's a bit more obvious. So you can go like this, and like this, and pause for 1 second. Dylan, this is the physics of skiing downhill. Small friction force holding you back, but not much because it's snow. What happens to the masses? In this equation, what happened to the mass? This is why a little kid and a grown-up can ski together and hold hands without the grown-up having to constantly adjust their speed like crazy. Now, at higher speeds, air resistance plays a big role because the grown-up has a bigger surface area. So I'm fibbing a little bit, but at medium and lower speeds, little kids and grown-ups can ski next to each other because the m cancels. Don't know if you've noticed or wondered why, but the other thing I like about this is, what were we trying to find, Hedrick? Have we got the a by itself already? Oh, great. It's going to be 9.8 sine 35 minus mu 9.8 cos. Hey, let's plug in the numbers. 9.8 sine 35 minus, what was mu? 0.2? 9.8 cos 35. I already know there's a built-in error check. It's got to be less than 9.8 because that'd be free fall. 4.02. Other possibilities. You could get a negative answer. The negative answer would just be telling you, you know what? Friction's so big, you're not going anywhere. You haven't defeated friction yet. In this case, although gravity's pulling it down, the car tires were enough to hold the car on the hill, thank God. Okay? So that's the other possibility. If you get a negative acceleration, check your math, check your numbers, but don't freak out. It might just mean you didn't go anywhere. 4.02 meters per second squared. You could have, but I did want to show you that the m would cancel. In fact, I think it's less work to drop the friction algebraic version in and have the m's cancel, because you get the a by itself automatically without having to divide. And the little nerd within me kind of likes that. I'm going to finish this next class, but already if you want to get a head start on the homework, and you don't have to because I realize, we want to go reading, we want to go reading. Fine, but questions you can try already, you should be able to handle number 1 and number 2. Don't hand those in yet. I'm going to assign more questions from this very important lesson, but if you want to tomorrow during flex or tomorrow night, if you want to try those 2 questions, you can.